Hey there, welcome back to Short Takes 331. Today we're going to talk about the Fourier transform, and this is part 2. And what I want to discuss in this video is what is the Fourier transform of a Gaussian curve. So I promised in the previous video that we're going to see the Fourier transform of a Gaussian, and that is because we studied in that previous video the Fourier transform of a delta and the Fourier transform of a single complex exponential, and we saw how they're related to each other and how one transforms into the other. Whether you start with the delta or if you start with the complex exponential, you go back and forth between those. And I made a reference in that video to the Gaussian and how the Fourier transform of a Gaussian is another Gaussian. And so that's me anticipating the result. And so let's derive it. So suppose we have this Gaussian curve. And whenever I say Gaussian curve, of course, I mean something like this. So we have a function that is given by some constant a times e to the minus x divided by sigma quantity squared. So this sigma represents the width of the Gaussian. You may find that sigma sometimes written outside here as sigma squared. Sometimes I've written Gaussian like e to the minus lambda x squared. It's all the same. It's just a quantity that represents the width of this Gaussian. And this a, of course, represents the height of the Gaussian at x equal to 0, where this factor is 1. So wherever here appears dividing the x in the exponent, wherever it appears dividing the variable, then is the width of the Gaussian. And so what we want to do is we want to take this function and insert it into our formula for the Fourier transform. So this is our formula for the Fourier transform. FTLD of k is our Fourier transform, and so is 1 over 2 pi integral between minus infinity and infinity f of x e to the minus ikx dx. And so we go ahead and insert that into our formula, and what we get, of course, is that the a pops right out. And so we get a divided by 2 pi integral between minus infinity and infinity e to the minus x squared over sigma squared. So now I took the square root of both. No particular reason for doing that. And then we have, of course, also in the exponent, minus ikx. And so the conventional way of doing this among physicists anyway is to go ahead and complete the square here. And so by completing the square, we mean what I'm about to do here. So let me set aside the minus sign, which we're going to need later, of course, and focus on these two terms then that are added together. So x squared over sigma squared plus ikx. So I can factor out the 1 over sigma squared, and so then I pay the price of multiplying by sigma squared on the second term here. And so now I rewrite this parenthesis by adding and subtracting a term. And also I'm going to go ahead and write explicitly this 2 here and divide by 2 to make it explicitly look like the square of something. And so what I like to do is then I copy the x squared, and then I take this term and I write it as twice something. So that something is x ik sigma squared divided by 2. This x is the same as this x, of course, but this whole term, this whole factor here, ik sigma squared over 2, is what needs to appear squared in order for us to have a perfect square. But if you add something, you have to subtract it as well. And so then just like this whole thing now gives us the perfect square that we want, which is x plus ik sigma squared over 2, this whole thing squared, we also need to now subtract this other thing, which is what appears here. So let's take a look at this. So it's minus, and then we have an I squared, which kills that minus sign, so that's why we get a plus sign here. And we have k squared, sigma to the 4th, and then 2 squared, which is this 4 here. Now it's y sigma squared because we had to divide by sigma squared here. And so then this extra term that appears on top of this perfect square is k squared sigma squared divided by 4. So very well. So now we take this and replace it by this in our exponent. And so we get the integral of e to the minus 1 over sigma squared, the perfect square, like I was saying. And then this factor that together with the minus sign that I said I left out and that appears here and here, now it just gives me a quantity that does not depend on x at all. So it factors out of the integral entirely. So now I have then this integral and then e to the minus k squared sigma squared over 4. So I'm allowed to do that. Again, this doesn't depend on x at all, so it factors right out of the integral. It appears in the exponent. Again, remember to keep track of your minus signs. That's a common mistake sometimes that I make sometimes. And so now we have this integral that we need to do, but you know, for our discussion, we don't really worry about it too much. In a way, we've already shown at this point that the Fourier transform of a Gaussian gives us another Gaussian here in k in the k variable. So k squared appears here. But let's do that integral, and if you do it, you can look. You can do it by shifting variables from y to, or rather from x to y. Y is x plus ik sigma squared over 2. So we call this whole thing y, And so then we have e to the minus y squared over sigma squared. The dy is also equal to the dx, because as far as the variable x is concerned, this is just a constant. And so dy is equal to dx. And so we can do this integral. It's a Gaussian integral like we've seen before. And so this is equal to sigma times the square root of pi. So remember, the sigma here appears dividing our variable, and so it should appear multiplying when we actually execute the Gaussian integral. There's a couple of videos in Gaussian integrals in this channel, so you can go take a look and see how that integral was done. But this is the result. And so the overall result then of our Fourier transform of a Gaussian is given down here. It's a over 2 pi sigma square root pi and e to the minus k divided by 2 over sigma, this whole thing squared. So why did I write this as 2 over sigma and this sigma squared over 4? Well, you could write this as k sigma divided by 2, the whole thing squared, but I like to divide by this. Why? Because remember what we said, that whatever appears dividing our variable is the width of the Gaussian. So this sigma is the width of this Gaussian, but down here in the Gaussian in k space, this thing is what appears dividing the variable. 2 over sigma is what appears dividing the variable. It's the same thing I wrote up here, but it's just rewritten so as to make it appear in the denominator. And so the width of this Gaussian then is 2 over sigma. So the width of the Gaussian in k space is 2 over sigma. So again, once we get to this point, in fact, already here, we have proven that the Fourier transform of a Gaussian is another Gaussian, but now we've identified the width. And the width is 2 over sigma, where sigma is the width of the original Gaussian. So if we call sigma x the width of the Gaussian in x space, and sigma k the width of the Gaussian in k space, then we find that sigma x is just sigma, and sigma k is 2 over sigma. Okay, so this object here, this 2 over sigma, is the Gaussian, the width of the Gaussian in k space. And so it turns out that the product of the two is always just 2. And it's completely independent of the width of the original Gaussian. And so the product of the Gaussians in x space and k space then is just 2. And that's always true. And this is what's connected to the uncertainty principle in quantum mechanics that I was referring to in the previous video. In quantum mechanics, coordinates, meaning x, and momenta, meaning k, are dual descriptions of a system that whatever system you're looking at, and they're connected by a Fourier transform. So there are two choices of basis in quantum mechanics. You can work in the coordinate basis, you can work in the momentum basis, and they're connected to each other by a Fourier transform. And so if you have a system that's described in terms of coordinates, so in the x space, and you have a good precision, meaning that sigma x is small, that means that you have a good knowledge of where the system is, then what will happen is that sigma k will be very large, because if sigma x is small, and sigma x times sigma k always has to be equal to 2, and sigma k has to be very large in order to compensate. And so you have this type of situation where if you have good knowledge of where the system is in x, then when you go to k space, you have no knowledge of what the momentum is. And again, this is simply a reflection of the uncertainty principle. And vice versa, if sigma k is small, if we have good knowledge of where of what the momentum is of the system, well-defined momentum, then sigma x, on the other hand, will be large. And so if we have well-defined momentum, we don't know where the particle is. So this property really holds regardless of quantum mechanics. It simply applies to waves or any signal you want to analyze with a Fourier transform. A signal that is very localized in one space will be highly delocalized in the other space. So no matter if you're talking about x space or k space, if it's localized in one space, it's delocalized in the other space, and vice versa. So that's almost all I have for you today. As an exercise, you should try to do the integral from minus infinity to infinity of our Gaussian factor. I simplified it here by taking sigma to be 1, because it doesn't add anything for this particular exercise. And so you can consider this integral e to the minus x squared, e to the minus ikx dx. This is, of course, a Fourier transform of this simple Gaussian. But you can try to do that by expanding the exponential as a power series. And by the exponential, I mean this exponential here, this complex exponential. Try to expand this one as a power series and use the knowledge of the Gaussian integrals that we have from previous videos. And then you can do each of those integrals for each of the terms in the power series expansion of this object here, of this factor. And then you can reconstruct and rebuild the result and find that indeed you get that this type of integral gives you a Gaussian now in k space with a width that is inversely proportional to the width of this Gaussian here, which is just 1. And that's it. That's all I have for you. I hope you're having a good time at this holiday break and you're staying safe and warm inside. It's very windy here in North Carolina. And as always, if you enjoy these videos, please consider liking and subscribing to the channel. And if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. And I'll see you next time.